In this section, we discuss how semiconductor diodes are changing the way we engineer lighting. We use a number of competing lighting technologies. The standard incandescent lamp has a resistive filament that uses the residential AC power directly to become glowing hot and produce light. Fluorescent lamps are more energy efficient and so became the technology of choice for high-use settings, but the cost of the bulb is greater, in part because of a ballast required to regulate the voltage. The development of efficient LED lighting is now making a major impact in the lighting industry and global energy usage. The technology has rapidly advanced so that LED chips can now be made for pennies. The energy savings is going to make a huge difference in the global energy usage and an important solution to mitigate climate change. While the physical concept of LED lighting has been around for a long time, it was really breakthroughs in material science that made the difference to enable commercialization of LED lighting, enough to get material scientists to win the Nobel Prize in Physics in 2014. Recall that visible light is a relatively narrow band of the electromagnetic spectrum where the human eye sensitivity varies significantly. It is maximized around green light, which is why green laser pointers seem so much brighter than other colors. Sunlight has a peak intensity in the visible wavelengths due to black body radiation from the 5000 K surface of the sun. The photographer's and movie projector's favorite lamp is the xenon flash bulb because they are bright with a flat spectrum, but they produce a lot of harmful UV light. The incandescent bulb is a hot filament that produces black body radiation. However, the typical incandescent bulb has peak intensity in the infrared and so produces a lot of heat and warm red-orange light. It has an equivalent temperature of 2700 Kelvin. Halogen incandescent lamps run hotter, around 3,000 to 4,000 Kelvin, and peaks in the visible, which makes it somewhat more efficient. The fluorescent lamp requires a voltage regulator or ballast to make an electric discharge in a mercury vapor. The ultraviolet light produced excites a phosphor that gives red, green, and blue light that appears white. The sharp peaks are due to atomic transition of defects in the phosphor, which are engineered to be at the right wavelength. LEDs very efficiently produce a narrow range of light determined by the band gap that also requires a phosphor to make white light. Cool white LEDs have a blue LED giving a narrow spectrum of blue light that also excites a phosphor to produce a broadband spectrum around yellow light. Warm white LEDs have more phosphor, particularly in the red, which makes them somewhat lower efficiency. For decades, the only LEDs that you could find easily were red LED. That is because 3-5 semiconductors that we could easily make then, such as gallium arsenide based, could be alloyed with elements such as aluminum and phosphorus, which increase the band gap into the red region. The smaller phosphorus and aluminum reduce the lattice constant, increase the bonding strength, and open up the band gap a little. Silicon and germanium have band gaps too small and are also an indirect gap, which is not good for LEDs. In order to excite a phosphor, you need a photon of higher energy than what the phosphor is going to emit. Frequency doubling mechanisms exist, but since it requires 2 photons or 2 electrons at the same place, it is much more unlikely to work and therefore inefficient. It is used in lasers, but not LEDs. In the 80s and 90s, there was much effort to develop the blue LED. Ultimately, it was the development of the materials processing for doped gallium nitride with sufficiently few defects that enabled the blue LED. LEDs work by driving electrons and holes to recombine across the band gap, which happens in a PN junction diode under forward bias. The N-type material has many electrons, while the P-type material has many holes. They can meet at the junction, recombine, and produce light. Recall that the band diagram of a PN junction has a uniform Fermi level when the electrons are in equilibrium, or no bias voltage. To have the Fermi level near the valence band on the P side and near the conduction band on the N-type side requires that the bands have been bent due to the built-in voltage. The built-in voltage V0 also acts as a barrier to charge transport preventing the diffusion of electrons or holes to the other side. Forward bias adds negative potential to the N-type side, pushing electrons into the junction, and positive potential on the P-type side, pushing holes into the junction. When there is a forward bias, the built-in voltage barrier is reduced, allowing the current to flow into the depletion region, which we call current injection. Injection of electrons and holes brings them close enough to recombine and produce light, called photoemission, with an energy approximately equal to the band gap. They can recombine in the depletion region of the junction, or if they don't recombine before they reach the other side, they become excess minority carriers and recombined later. This often happens in the lighter doped side, here the p-type region, where some of the many electrons from the heavily n-type doped side, denoted N+, make it to the p-type side and recombine there. A diode primarily produces light with wavelength determined by the band gap. This is much more efficient than an incandescent lamp, which produces the whole spectrum of light, including infrared heat and ultraviolet light. One challenge is how to get the light out before it excites other electron-hole pairs, as the wavelength just produced will easily get absorbed by other parts of the semiconductor to make electron-hole pairs elsewhere. The trick used to produce the light near a p-n junction, but not have the light absorbed by the rest of the semiconductor, is to use a double heterostructure. The idea is to make a thin film of material with the band gap you want, here 1.4 eV gallium arsenide, called the active layer, in between materials with a larger band gap, here 2 electron volt aluminum gallium arsenide. Again, the structure is a diode with one side p-type doped and the other n-type. The active layer here is lightly p-doped. Here we actually want the electrons from the n-type side to quickly move to the NP junction and recombine in the active layer. Under forward bias, the driving voltage pushes the electrons from the n-type side into the active region, where they recombine and produce the light. When the electrons and holes are driven together to recombine in the gallium arsenide layer, they produce 1.4 eV light that is not absorbed by the 2.0 eV aluminum gallium arsenide, and so can escape the device with little absorption loss. The larger band gap is also a confining layer, as it helps contain the injected electrons in the active layer until they recombine. Notice the difference in band gap appears mostly as a conduction band offset at the p-type gallium arsenide aluminum gallium arsenide interface, which acts as a barrier for electrons, keeping them in the active region. We also have to consider the metal interconnects as well, because metals will typically reflect or absorb light. On the back side, we actually want a metallic reflecting electrode to reflect light that is produced heading to the right. Especially in organic LEDs or OLEDs, a transparent conducting oxide TCO is used for the left electrode to supply electrons but allow visible light to pass through. The output spectrum of an LED will have some width to it that we can understand from the band structure and electron distribution function. Recall that the distribution of electrons and holes are centered near the band edges, but that the number of electrons is actually small at the exact band edge because the DOS is small there. There are more electrons at slightly higher energy, where the peak number of electrons is about 1/2 kT above the band edge. Because the efficient direct transitions are vertical in the E versus K diagram, the lighter band is going to run out of electrons or holes states sooner. The emission spectrum should look like what we call the joint density of states, considering all the possible transitions of possible electrons to holes, which is a convolution of the valence band density of states, the conduction band density of states, and the distribution function. One way to get a sharper LED spectrum is to use a quantum well. Here, the active layer is so thin, less than 50 nanometers, the electron wave functions are confined, like in the finite potential well problems we solved in Chapter 3. The conduction band minimum is the lowest energy a free electron can have, acting like the potential V we use to solve for particle-in-a-box wave functions. Likewise, the valence band maximum acts like a potential well for holes. The smaller band gap in the active layer leads to a band offset and the potential well for both electrons and holes. Instead of free electron-like band states, the states in the well region are quantized to particular energies because the well is so narrow. The quantized states are called subbands here as they still have free electron-like dispersion in the other two directions. They are only quantized in the thin direction. These electrons are called a 2D electron gas because they are confined so that they only move freely in two dimensions. Recall that even the n=1 state has energy a little above the bottom of the well. The quantization limits the possible transitions, and so a more narrow spectrum of light is produced. The quantum wells also help trap electrons and holes, giving them time to recombine without continuing into the other region, so that the quantum wells improve the quantum efficiency of the LED. Because the energy of the well states depend on the well width, the wavelength of quantum well LEDs can be tuned by changing the thickness of the well without having to change the band gap of the base material. Modern LEDs are typically multi-layer devices. The heterostructure LED has an active layer surrounded by layers with a higher band gap so the light can get out. The confining layers with higher band gap need to be doped sufficiently to inject the electrons and holes. The thicker substrate holds all the layers together. In this case, gallium arsenide substrate is used to make the aluminum gallium indium phosphide based layers. The gallium nitride quantum well LED uses an aluminum oxide sapphire substrate to grow the gallium nitride as a barrier and the indium gallium nitride with a smaller band gap to make the quantum well. Here, a thick gallium nitride layer is grown first, where the interface with the sapphire substrate has many dislocations, which is avoided by placing the negative electrode above it. Multiple quantum wells are typically fabricated to increase the light intensity. The substrate also enforces all the layers to be lattice matched, meaning that all the atoms are in a specific crystalline arrangement with the layers below called epitaxy. To keep the LED efficiency high, the defect density needs to be low because defects act as non-radiative recombination sites and reduce charge carrier mobility. We use epitaxy to grow crystalline films on a single crystal substrate such as silicon, gallium arsenide, aluminum oxide sapphire, MgO, etc. The crystalline atomic arrangement of the substrate helps align the atoms as they arrive onto the surface. In molecular beam epitaxy, the atoms are often evaporated from a heated source, but other deposition techniques such as chemical vapor deposition, pulsed laser deposition, and sputtering also produce epitaxial films. When individual atoms or molecules arrive, they are quite mobile and can move around on the surface to find a step edge to grow the crystalline film. The film crystal tends to be crystallographically oriented with the underlying crystal, making it epitaxy. If the lattice is exactly the same, like the same material or homoepitaxy, there should be no strain. In general, with a different material, there will always be some lattice strain because the film lattice would rather be bigger or smaller than the substrate. For very thin films, the strain energy is small, so the films are easily strained, which can give different properties. Strained silicon is becoming important for semiconductor devices. Depositing silicon on a silicon germanium substrate with a larger lattice constant strains the silicon, which increases the electron and hole mobility by decreasing the effective mass and reducing electron scattering. The strain energy can be relieved by forming dislocations. Here we see the threading dislocation formed in gallium nitride just above the sapphire substrate. The film deposited above can then be strain-free and without dislocations, perfect for an LED. In any design problem, you want to be clear as to your customer's performance metric to guide material selection and engineering. At the material level, the metric might be the internal quantum efficiency, which is the fraction of recombining electron and hole pairs that actually leads to photons with the desired wavelength. At the heterostructure level, your metric may include the ability of the light to make it past the confining layers and the electrodes, which is the extraction efficiency. So the external quantum efficiency is the product of the extraction efficiency and the internal quantum efficiency. Or the customer could be concerned about the power conversion efficiency. the net optical intensity produced per electrical input power that could include transformer and resistive losses in the entire device. Maybe the appropriate metric is the intensity of light visible to the human eye, measured in lumens per input power. Here, the spectral intensity of the human eye is needed and the conversion of watts of optical power to lumens. Another limit to the extraction efficiency is the internal reflection of the light as it escapes the semiconductor chip. This is due to the index of refraction change as the light moves from the high bandgap semiconductor to the air. The reflection is worse for higher incident angles, reaching total internal reflection at high angles. To mitigate this problem, a hemispherical plastic dome is formed over the diode so that when the light escapes from the dome, it is at a low incident angle. Texturing the surface of the semiconductor also helps extraction of light from the diode chip. The common LED design for indicator lights includes a reflecting cup to focus the light forward and a molded epoxy lens to minimize internal reflections. Bright white LEDs are commonly surface-emitting diodes with a yellow phosphor coating that can be easily attached to a heatsink for cooling the high-power LED. Wire bonds need to be attached, which is another expense and potential point of failure. The transparent dome protects the chip and acts as a lens to improve extraction efficiency. By engineering an optical cavity around the active layer, the light emission can stimulate further electron-hole recombination, which is the basis of a laser. Whereas spontaneous electron-hole recombination leads to light with random direction and phase, stimulated photoemission produces light with the same phase and direction as the stimulated light. The resultant light has superior coherency, which enables the beam to remain narrow over large distances and allows extremely short pulses for the use in optical scanners, memory, and communications.